Okay, now let's take a look at maybe a more useful application of conservation of momentum. And one that we don't have necessarily a perfectly elastic or a perfectly inelastic collision. And now collisions don't have to be elastic or inelastic in order for momentum to be conserved. It is conserved in every case. Those were elastic and inelastic were just special cases here. So in this exercise, we have a bullet shot into a block, and then the bullet goes through the block, and then we're given some information about the speed of the bullet after it emerges. So just looking at this, knowing that I have some collision going on here, I'm going to go ahead and start out with a conservation of momentum. So I'll start with a coordinate system like this, and before we have there's like a block here, and this block has a mass of 1.12 kilograms. And then we have a bullet over here, and it has a mass of 4.25 grams. Let me actually say here, I'm going to call this a crate instead, MC for crate. That way I can use different subscripts. So the mass of the crate is 1.12 kilograms, and then mass of the bullet, this is 4.25 grams, so 0.00425 kilograms. So we have some consistency there. The bullet was first traveling off at 375 meters per second, then it hits the block, goes through it, comes out at 122 meters per second. So the velocity of the bullet is equal to 375 meters per second. And then in the after condition over here, we have the crate and the bullet have the same masses. I guess it's possible, likely, that the block or the crate lost some of its mass, sawdust or something, but let's pretend like that's not the case. And so we still have a 1.12 kilogram crate, and now the bullet's out here with same mass, and now it's traveling at 122 meters per second. And the question is, how fast is this crate moving after? So what is the final velocity of the crate, VC final of the crate? It said that it was initially at rest, so we know the initial velocity of the crate was equal to 0. So we have a collision, and we can use momentum in any collision. The two things that are colliding are the bullet and the crate. And so we can write out the momentum of the system before the collision and the momentum of the system after. So our initial momentum, this is going to be mass of the bullet times velocity of the bullet plus mass of the crate times velocity of the crate. And this will be equal to the final momentum, which is equal to the mass of the bullet times the velocity of the bullet plus mass of the crate times velocity of the crate. With all these velocities are vectors. Okay, so the initial velocity of the crate was 0, so it simplifies this one down quite a bit. And actually, maybe I'll just algebraically write this out here. The question is, how fast is the block moving just after the bullet emerges from it? So we're looking for the velocity of the block here, right? Oh, sorry. That's B is for bullet, C is for crate. That's why I chose different subscripts. We're looking for this one. So with both of these momentums, the initial momentum equal the final momentum, I can algebraically solve for the velocity of the crate. We have velocity of the crate in the final condition. This should have been final, and this should have been initial. This is going to be the mass of the bullet times the initial velocity of the bullet minus the mass of the bullet times the final velocity of the bullet divided by the mass of the crate. Oh, that's not a vector. Okay, So this is what we would have for the final velocity of the crate. And so then plugging in, actually you can even factor out a mass of the bullet. We have the final velocity of the crate would be equal to 0.00425, the 4.25 grams, times 375 minus, what was the speed it emerged, 122. Divided by 1.12, and we have the final velocity of the crate is equal to, this is 0.96 meters per second. And this would be the velocity of the crate immediately after the collision. The exercise told us, just for simplicity for now, that it was on a frictionless surface, level frictionless surface, so horizontal and frictionless, so mu is equal to 0. But even if we did have friction here, this would be the velocity of the crate immediately after the collision. But because there's no friction and it's level, this would be the velocity of the crate some indefinite time after, because there's no friction to slow it down. So the thing I guess to note here is that the momentum, if you actually look at this, here, let me write it out this way, get rid of this MC, let's just write it back here. This is the momentum of the crate in the final condition, and this is the change in momentum of the bullet between the initial and the final. Right? So the momentum gained by the crate is the momentum lost by the bullet. Right? So then that's, that makes sense for conservation of momentum. Whatever momentum was lost by the bullet is what the momentum was picked up by the crate. And then given the fact that we had the mass of the crate, we were able to find out its final velocity of the crate.